In today's lesson, we are going to be solving linear systems graphically. Now, this is going to be a little bit of a review from the previous lesson and from grade 9. We're just going to look at maybe some different examples again, just to kind of get that refresher of equations of lines and how to graph them. Because again, it will help us as we go forward in this unit. So the main thing that we're doing, or the main thing this whole unit focuses on, is a linear system or linear systems. Now, a linear system is two or more linear equations that are considered. Right? And what that means is really we try to solve these two or more equations at the same time. Essentially, what we're looking for is when are the values the same. So that means we're looking for a point of intersection. We're looking for where the two lines cross, right? And the point of intersection is found on both lines, and these lines have the same values at that point, right? So regardless of whatever the values are, if the two lines cross at that point, those values are going to be the same in either equation. So say if the point of intersection is when x is 3, that means the y value is going to be the same for both of those equations as well. And the point of intersection is what we call the solution to the linear system. Right, so kind of we see here, right, the lightsabers are crossing. Where they cross, that's considered the point of intersection or the solution. Now, depending on what types of lines we have, we could have a couple different scenarios. Right, so we could have some scenarios where there is one solution, right? Two lines cross, they cross at one point, and then they drift off forever without touching. You could have two parallel lines, right, that never cross, so there is no solution. And there might be an infinite number of solutions, which means the two lines are exactly the same. They're on top of each other, meaning they cross an infinite number of times. Right? So these are the three different kind of solutions that we might come across. So we're going to solve the following linear system by graphing. So again, we kind of reviewed how to graph equations of lines, both in y equals mx plus b form as well as standard form. We've looked at that in a previous lesson. That's all we're going to be doing today in this lesson, graphing the two lines and seeing where do they cross. So I have two lines here, 2x plus y equals 5 and y equals 2 over 3x minus 3. So I'm just going to label them equation 1, equation 2. Now equation 2 is already done. It's in y equals mx plus b form, and that's kind of the form we want to stick to because it does give us some useful information. It's what we're used to from grade 9, and it does make it easier for us to graph. So equation 2 is kind of already done. We don't really need to do anything with that. Equation 1, though, we do need to rearrange this to get it into y equals mx plus b form. So in order to do that, I'm just going to rewrite the equation here, 2x plus y equals 5. And what I'm going to do is I want to get the 2x over to the other side. So there's different ways you can think about it. You can think about it as, I'm just going to move it over to the other side of the equal sign, and it becomes the opposite. So y equals negative 2x, and there's a positive 5. Or you could think of it as canceling out minus 2x from one side, minus 2x from the other side. One side cancels out, and so on. So whichever way is easiest for you to remember, or whichever way you prefer. I'm more of a fan of just saying, okay, I'm going to move it to the other side. It becomes the opposite. Less work, or not less work, but less things you have to write down, less things you have to show. But I've been doing this for a long time. So you might need to show that you subtract 2x from both sides and one side cancels out, right? You might need to do that for a while before you become comfortable with showing the movement or kind of skipping that movement. So whichever way you choose to do, we now have turned it into an equation in y equals mx plus b form, which is what we want. Because now, in both cases, we can find our m value, or our slope, so negative 2, and our b value, or y-intercept. So m equals 2 over 3, and b equals negative 3. With those two values, we should be able to graph our lines. The b value tells us the starting point. So I'm going to start with equation 1. So b is 5, so that is my starting point. I'm going to start at 5. Now remember, for the next part, our m value tells us the slope. And for our slope, we need a rise over run. So for our m value for equation 1, it's just -2. Right? So I want to turn that into a fraction for the rise over run. And remember, anytime we have a fraction, or a whole number, sorry, for our slope, to make it a fraction, we just put it over 1. So that now gives us our rise and our run. And that will help us graph the next points. Because the rise of -2 tells us we go down 2, and a run of 1 tells us we go in the positive direction 1, like we've done here. And then we just repeat that pattern to the next point. And as soon as we have a couple, we can probably figure out the rest because it needs to form a straight line. So it's kind of going to be in the same spot or a repeating pattern. Once we have enough points, we can graph our line. Again, ideally, you want to have 3 points to get a nice, decent line. We're going to draw arrows at the end to show that the line goes on continuously in both directions. And we're going to go through, I'm just going to put a 1 there. We're going to go through and we're going to graph the next line. So equation 2, b value or constant of -3, I'm going to put a point there. My slope or my m value is already in a fraction form, so I already know what my rise and my run is. So my rise is up 2, so I'm going to go up 2, 1, 2, and my run is 3 or +3, so I'm going to go 3 to the right in the positive direction, and that's where my point is, or my next point is. I'm going to continue that pattern, 1, 2, over 3, so we kind of can map it out. I can reverse it, right or left 3, down 2, and I have my line. Now, you might have said, oh, well, why did we need to go through and graph all the rest of the points? We already found where it crossed right after the first movement, right? That first point we did here, I'll highlight it. That first point there, we already found that, right, with that first move. And you're right, you don't probably need to go any further. You can make the line as you, based off of those 2 points, because the main thing is you found the solution or the point of intersection. Oops. So in this case, if we're just looking for the solution or trying to solve the system, you're right. Right, we have our point of intersection. Our point of intersection is the point 3, -1. So we can just say then, therefore, the solution or the POI is 3, -1. So that is what we're looking for. That is solving the system, right? That's the solution. The next example, B, similar idea, except we have 2 equations now that are not in y equals mx plus b form. I'm just going to write them out. So 1 and 2, so they're not in y equals mx plus b form, so we need to go through and we need to convert them into that form. So I'm going to start with the first one, 3x plus 2y equals 6. So again, our goal is to get y on one side and everything else on the other side. So I'm going to move the 3x over to the other side. So I'm going to get 2y equals -3x plus 6. Nothing changes to that 6. It's still on the right side. Now, you might say, oh, well, I have everything on one side and y on the other, so I'm done. But remember, when we're trying to get it into the equation of a line form, we need to get rid of any values in front of the y, aside from 1. So in this case, we have a 2 here. So I want to get rid of that 2. Now, remember, the operation between a constant or a value and a variable, or a number and a variable, is multiplication. So this is actually 2 times y. So to cancel out the multiplying by 2, we need to divide by 2. And what we do to one side, we have to do to the other side. So I have to divide the entire right side by 2 as well. So the one side, it cancels out, and I'm left with y. And on the other side, both values or both terms are divided by 2. So that means negative 3x divided by 2 and 6 divided by 2. So I can split it up like that. I can simplify part of it. I can't simplify the negative 3 divided by 2 because that doesn't simplify nicely. And I want to leave my slope as a fraction to find the rise over run. And then 6 divided by 2 is 3. Do the same thing for equation 2. X minus 2y equals 10. Let me just move everything over just a bit to fit it nicely. So I'm going to move the x over so it becomes negative x. So negative 2y minus x plus 10. The negative or the minus in front of the 2 stays, right? Because that's attached to the 2, not the x. The x becomes negative when we moved it across. We're going to divide the one side by negative 2 to get y by itself, and we divide the other side by negative 2 as well to keep things balanced. So one side cancels out. We are left with y equals negative x divided by negative 2 plus 10 divided by negative 2. Now that middle step that I just did, you don't need to write that out if you're comfortable doing that division in your head, or moving to the next step and doing it kind of on a calculator. So you might be able to skip that step. So negative x divided by negative 2 is going to be positive x over 2. Or if it helps, it'd be positive 1 over 2x. Just a different way to represent it. And then positive 10 divided by negative 2 is negative 5. So now I have the second equation in y equals mx plus b form. In both equations, I want to find the m and the b value to help me graph it. So for equation 1, m is negative 3 over 2, and the b value is 3. For equation 2, m is 1 over 2, and the b value is negative 5. Now that I have that information, I should be able to graph those two equations. So for equation 1, b is 3, so I'm going to put a point at 3. I'm going to use the rise over run. So go down 3 over 2. And that is my next point. And just repeat that pattern to get more points, or repeat that movement to get more points. And I'm going to draw or connect the points to create a line. So there is equation 1. Equation 2, I'm going to do the same thing. B is negative 5, so I'm going to put a point at negative 5. And I'm going to use the rise over run to go over or up 1 and over 2. There's my next point. I'm going to repeat that pattern, up 1 over 2. I could say, okay, well, that point is on the line as the other one. It's a common point, right? So I could continue the pattern if I wanted to, but I had 3 points. I had enough to find the point of intersection. I was able to map it onto there, and I have enough to draw a straight line too, so I can only kind of end there with the 3 points. I don't need to go any further. So I found my point of intersection, or I found where the lines cross with the point of intersection, which is the point 4. So we go, x value is 4, y value is negative 3. So therefore, the point of intersection is 4, negative 3. Or the solution is 4, negative 3. The next example, we're going to look at kind of a word problem, right? So we might want to do this, we might apply this to real life situations where we're comparing costs between two different options, and we're trying to see which one's better or under which situations each one is better. Right, so Rick is planning on upgrading his internet plan. He compares the cost of 2 monthly plans and data overage charges. So Rogers is $100 plus $10 per 1 gigabyte over, and Bell is $140 plus $5 per 1 gigabyte over. So first thing we want to do is we want to write an equation for the cost of these plans. And so for our equation, it should be something in the form y equals mx plus b. Right? Anytime we come up with an equation, it should be something along those lines. So we need to find a multiplier and a constant, a slope or a rate of change, and a starting value or an initial value. So for Rogers, we really only see two numbers, 100 and 10. So really, if we're plugging in a value for m and a value for b, you have a 50-50 shot. So you have to think about, okay, which one is my initial value or my starting value? Well, the initial value, what we're starting with, is 100. So that's going to be our b value. So it's going to be plus 100. The next value is going to be your rate of change. And it also helps because we see that keyword per. So it's $10 per 1 gigabyte. So that's the rate that our value is going to be changing, and that's the rate that the cost is going to be changing. $10 per 1 gigabyte. So that would be 10x. For Bell, if we kind of use what we just did with Rogers, I'll use a different color. Y equals, again, if it helps, we're going to start with 140. So 140 is our base fee, our initial value, our starting value. And our rate of change is going to be $5 per gigabyte. Now that I have these two equations, right, I have my m and my b value. Right, so for Rogers, my m value is 10, my b value is 100. And for Bell, my m value is 5 and my b value is 140. So again, that should be enough for me to go through and graph my points or graph my lines. So Rogers, probably should have used red, but anyways, keeping it consistent with the rest of the note. B is 100, so I'm going to put a point starting at 100, and M is 10. So that means for every 1 gigabyte over, we are going up $10. So that means my points are going to look like this. Each tick going up represents 10, right? And each tick going across represents 1 gigabyte. So this would be dollars and this would be gigabytes. So you want to be careful and think about what the scale is, right? In the other ones, every square represented 1, but here every square represents 10. So we want to be mindful of what the squares represent. We don't still want to assume that they're equal to 1. I'm going to draw my line. I'm going to put arrows. So this is Rogers. Next, we are going to do Bell, which is the next equation. So we have B as 140. So I'm going to put a point here. And my M value is 5. So now this one's going to be a little bit harder. Right? It's going to be a little bit harder because how do I go up 5 for every one? It's going to be like halfway between there. So you could do that. Or we could think, okay, 5. Right? We think of that as a fraction. 5 is the same as 5 over 1. Now, what's an equivalent fraction? Well, we could say 10 over 2. Right? So that would mean $5 per 1 gigabyte or $10 per 2 gigabytes. That's equivalent. That's the same thing, right? And when I represent it as a different fraction, it gives me another rise over run that I can use. So it kind of skips over a point. But in terms of graphing it, it's going to still give me the same line, right? So if I go up $10, so that's up 1 tick and over 2, that allows me to put a point in without having to kind of go through and kind of estimate, oh, halfway is here, so there should be a point there. Now you can do that. It's not wrong. You just might not be as accurate as you want to be when graphing your lines. So go through like that. And now I'm going to graph my lines or my line. Technically, you don't have to have the line extend beyond the y-axis because in this scenario, We don't have any value less than 0 gigabytes, right? Overages only start after 0, so we could remove or we don't have to draw the lines going beyond the y-axis, but again, personal preference. But for this situation, we don't need to. So we've graphed it, right? We wanted to solve the system, so we want to find where do they cross. So here. So we found our point of intersection. We see where the lines cross. In this case, it is nicely at, what is that? 6, 7, 8. So when at 8 gigabytes over, it is costing us 50, 60, 70, 80. So $180. So therefore, the POI is 180, or sorry, not 180, it's 8, 180. So that means if you go over 8 gigabytes, the cost is the same. Right? So now we know that kind of break even, not that break even, but we know at what value are they similar or the same. As well, by graphing, we're able to see when is it better to maybe choose one of the options over the other. Right off the bat, I'd probably say as long as everything else is considered the same, I would choose Rogers if I'm not going to use more or go over by more than 8 gigabytes. If I find that I'm going to be going over 8 gigabytes or overages, I'm probably going to want to go with Bell because in the long run it's going to be cheaper. So it all depends on the different situations, but we can graphically or visually see those different situations, not just when they're the same. And lastly, determine whether or not this point is a solution to the given system. So we kind of looked at this before in a previous lesson, review lesson, but essentially what we want to do is, does this point exist? So does -3, 2 exist on the lines? So we need to see, does that point exist on these lines? Now you could graph them if you wanted to and see, okay, is -3, 2 one of those points, right? But an easier way that we did look at before is, and again, we're going to take each equation, and we have to take both because it has to be on both lines. Actually, let me rewrite that and we'll highlight it. Exist on both lines. So it needs to be on both lines, not just one. It needs to be on both. So we're going to take each equation. I'm going to start with the first one. And I'm going to plug in the values -3 and 2. -3 representing the x value, 2 representing the y value. So I'm going to replace the variables with those values. So it would be 3 times -3 plus 2 times 2 should equal -5 if it is on the line. -3 times 3 times -3 is -9, plus 4 equals -5, -5 equals -5. It does, so that point is on the first line. That's good. We do need to make sure that it's also on the second line. So I need to take the second equation, -x plus y equals 4, and do the same thing. Take those points and plug them in. So -x or -3 plus 2 equals 4. So -3 is +3 plus 2 equals 4. We have 5 equals 4. 5 is not 4, so that does not work. So that means since it's on one equation and not the other, therefore -3, 2 is not a solution. So that is how we can check. So so going back to all the ones that we looked at, if we wanted to double check that these point of intersections were correct, we could plug them into each equation and we should get that they exist on both, right? So all these POIs we could double check if we wanted to, although graphically we've kind of proven that they are, but just maybe in case we drew our graphs wrong or we're not sure if we drew them correctly, we can always take the point or the POI, plug the values back in, and solve to see if left side equals right side, or to see if it satisfies the equations for both parts. And again, most of this should be a little bit of a review, at least in terms of graphing lines. That is something that you should have looked at in grade 9, and we did review it in lessons previously. So this is just kind of extending that.